Imagine standing on a platform, not on Earth, but in the vast expanse of space, looking down at our planet from a vantage point hundreds of miles up. This isn't the stuff of science fiction. It's a vision of the near future, where space elevators and orbital habitats could become a reality. These aren't your average skyscrapers or space stations. We're talking about structures so massive, they'd make the Burj Khalifa look like a child's building block. A space elevator, stretching from the ground to geostationary orbit, would be a marvel of engineering, a ribbon of carbon nanotubes and steel, defying gravity itself. And orbital habitats? Picture massive wheels spinning in space, creating artificial gravity, where people could live, work, and play among the stars. The physics behind these structures is mind-bending yet simple in concept. A counterweight at the end of the space elevator, perhaps a captured asteroid, would balance the entire structure, keeping it taut and stable. It's not just about the view, though. These structures could revolutionize space travel, making it cheaper and more accessible than ever before. So buckle up. We're about to explore the incredible world of space elevators and orbital habitats, where the sky is quite literally not the limit. The dawn of a new era in space infrastructure. The concept of space elevators and orbital habitats has long been a staple of science fiction, but recent advancements in materials science and engineering are bringing these ideas closer to reality. A space elevator, in its simplest form, is a long, strong cable extending from the surface of the Earth to a point in geostationary orbit. This cable would serve as a highway to space, allowing for the efficient and cost-effective transport of people and materials. The sheer scale of such a project is staggering. The cable would need to be thousands of kilometers long, with a counterweight at the end to keep it taut. This counterweight could be a massive space station or even an asteroid captured from the solar system. The view from an orbital habitat at the end of a space elevator would be breathtaking. From this vantage point, the Earth would hang below, a blue and white marble suspended in the blackness of space. The curvature of the planet would be clearly visible, and the thin line of the atmosphere would be discernible. The stars would be ever-present, unobscured by the atmosphere, and the sun would rise and set with a regularity dictated by the habitat's orbit. This perspective would offer a profound sense of our place in the universe, a humbling reminder of the Earth's beauty and fragility. The physics behind space elevators and their counterweights is fascinating. The cable must be strong enough to support its own weight and the weight of the payloads it carries. This requires materials with exceptional tensile strength, such as carbon nanotubes or graphene. The counterweight at the end of the cable serves to keep it taut, using the centrifugal force generated by the Earth's rotation. This force pulls the cable outward, counteracting the gravitational pull that would otherwise cause it to sag. The counterweight must be massive enough to generate sufficient centrifugal force, but not so massive that it becomes impractical to launch into orbit. Orbital habitats, like those envisioned by the late physicist Gerard O'Neill, would be massive structures built in space to provide living and working environments for large numbers of people. These habitats could be cylindrical or spherical in shape, rotating to generate artificial gravity. They would be constructed from materials launched from Earth or mined from asteroids. The interiors would be designed to mimic Earth-like environments, with parks, gardens, and bodies of water. These habitats would not only serve as homes for space-based industries, but also as waypoints for missions deeper into the solar system. The construction of such habitats would be a monumental task, requiring advanced robotics and automated systems to assemble the necessary components in the harsh environment of space. Historical context, from fiction to feasibility. The concept of space elevators and orbital habitats has evolved from the realm of science fiction into a subject of serious scientific study and engineering discussion. Initially popularized by authors like Arthur C. Clarke, the idea of a space elevator, a structure extending from the Earth's surface into geostationary orbit, has captivated imaginations for decades. The sheer scale of such a construction is mind-boggling. A space elevator would need to be tens of thousands of kilometers long, dwarfing any man-made structure ever built. The tether, or ribbon, would need to be made of materials strong enough to withstand the immense tensile forces, likely utilizing advanced materials like carbon nanotubes or graphene. From orbit, the view would be breathtaking. The Earth would sprawl beneath, a tapestry of blues, greens, and whites, while the stars would shimmer in the blackness of space. The space elevator would serve as a gateway to the cosmos, a permanent, reusable infrastructure for transporting people and cargo into space. The physics behind such a structure relies on a counterweight placed in geostationary orbit, about 36.0 kilometers above the Earth's equator. This counterweight would balance the centrifugal force exerted by the Earth's rotation, keeping the tether taut. The elevator would climb up the tether, powered by lasers or other advanced propulsion systems, reaching the top in a matter of days rather than the hours it takes for a rocket to reach orbit. Orbital habitats, on the other hand, would be massive structures built in space, potentially housing thousands of people. These habitats would rotate to create artificial gravity, making life more comfortable for long-term residents. The scale of these habitats would be enormous, with diameters of several kilometers. The view from an orbital habitat would be even more spectacular than from a space elevator. The Earth would fill the sky, a majestic blue and white marble suspended in the void. The stars would be visible even during the day, their brilliance undimmed by the atmosphere. Life in an orbital habitat would be a unique experience, a blend of the familiar and the alien. The feasibility of these concepts has been studied extensively. Engineers and scientists have identified numerous challenges, from the development of ultra-strong materials to the management of space debris. However, the potential benefits are immense. Space elevators could drastically reduce the cost of accessing space, making it possible to build large-scale infrastructure in orbit. Orbital habitats could provide a solution to overpopulation and resource scarcity on Earth, offering new frontiers for human expansion. The journey from fiction to feasibility has been long, but the dream of a spacefaring civilization is closer than ever to becoming a reality. The concept of space elevators. Space elevators represent a revolutionary concept in space travel and infrastructure. At its core, a space elevator is a proposed structure designed to transport material from the surface of a planet into space. The most studied design involves a cable anchored to the Earth's surface, extending up to a counterweight in geostationary orbit, approximately 36.0 kilometers above the equator. The sheer scale of this construction is mind-boggling. The cable alone would need to be several times longer than the tallest man-made structures on Earth, and its strength would have to be extraordinary to withstand the immense forces acting upon it. The view from a space elevator would be nothing short of breathtaking. As you ascend, the curvature of the Earth becomes increasingly apparent. The atmosphere thins, and the sky transitions from the familiar blue to the deep black of space. Cities and landscapes shrink to tiny, intricate patterns below. The International Space Station, for instance, orbits at about 400 kilometers above the Earth's surface, providing a stunning vantage point. However, a space elevator would offer an even more expansive perspective, allowing passengers to see the planet in its entirety, much like the astronauts on the ISS, but from a much higher altitude. The physics behind space elevators is both fascinating and complex. The key to making a space elevator work lies in the concept of a geostationary counterweight. This counterweight, positioned at the end of the cable in geostationary orbit, ensures that the cable remains taut and stable. The centrifugal force generated by the Earth's rotation keeps the counterweight in place, effectively pulling the cable upwards. The cable itself would need to be made of a material with an incredibly high tensile strength, such as carbon nanotubes or graphene, to withstand the immense tension and prevent it from snapping under its own weight. The elevator cars would then travel up and down the cable, powered by lasers or other advanced propulsion systems, transporting people and cargo into space efficiently and cost-effectively. Key components: the tether, anchor, and climbers. The tether, a ribbon-like structure, is the backbone of a space elevator. It stretches from the surface of the Earth to a point in geostationary orbit, about 36.0 kilometers above the equator. This tether must be incredibly strong and lightweight, capable of withstanding the immense forces exerted by the Earth's gravity and the centrifugal forces of the rotating Earth. Current concepts envision using materials like carbon nanotubes or graphene, which possess the necessary strength-to-weight ratio. The sheer scale of this construction is staggering. For perspective, The tether would be several times longer than the tallest man-made structures on Earth, dwarfing even the Burj Khalifa. It would be visible from the ground, a thin, shimmering line reaching up into the heavens. At the Earth's end of the tether is the anchor, a massive structure designed to keep the tether stable and secure. This anchor would likely be a large, mobile platform capable of moving to avoid weather and other potential hazards. The anchor's design is crucial, as it must distribute the immense tension of the tether evenly to prevent any weak points. From the anchor, climbers would ascend the tether, carrying payloads into space. These climbers are essentially robotic vehicles equipped with mechanisms to grip and move along the tether. They would use a combination of techniques, including laser-powered systems, to slowly ascend. The journey would take days, but it would be far more energy efficient than traditional rocket launches. The view from an orbital habitat at the end of the tether would be breathtaking. From this vantage point, the Earth would loom large, a vast, blue and green marble suspended in the blackness of space. The curvature of the planet would be clearly visible, with city lights twinkling in the darkness below. The tether itself would stretch down, a thin line disappearing into the Earth's atmosphere. The physics of the counterweight at the top of the tether is fascinating. It's not just a simple weight, but a dynamic system designed to balance the forces acting on the tether. The counterweight would likely be a large mass, possibly a captured asteroid or a specially constructed object, placed at the end of the tether in geostationary orbit. This counterweight ensures that the tether remains taut, providing a stable path for climbers to ascend and descend. The centrifugal force of the Earth's rotation keeps the counterweight in place, creating a delicate balance that allows the space elevator to function. Materials science, the quest for the perfect tether. The quest for the perfect tether in space elevator design is a formidable challenge, driven by the need for materials that can withstand immense tensile forces while remaining lightweight and durable. The tether, or ribbon, of a space elevator must stretch from the surface of the Earth to geostationary orbit, a distance of approximately 100 kilometers. This ribbon would experience tremendous stresses, including gravitational forces, dynamic loads from ascending and descending vehicles, and the harsh conditions of space. To put this into perspective, the tether would need to be strong enough to support its own weight over this vast distance, a feat that requires materials with tensile strengths far exceeding those of any known substance today. Carbon nanotubes are often touted as a potential candidate for the tether material. These cylindrical structures, made of carbon atoms arranged in a hexagonal lattice, possess exceptional strength and stiffness. In theory, a carbon nanotube tether could achieve the necessary strength-to-weight ratio. However, producing such a tether on the scale required presents significant challenges. The manufacturing processes for carbon nanotubes are still in their infancy, and creating a ribbon that is both defect-free and of sufficient length is a daunting task. Additionally, the behavior of these materials under the extreme conditions of space is not yet fully understood. The view from an orbital habitat anchored to a space elevator would be breathtaking. From this vantage point, the curvature of the Earth would be clearly visible, with the atmosphere appearing as a thin, fragile blue line. The stars would be visible even during the day, and the sun would rise and set with a frequency determined by the habitat's orbital period. This perspective would offer a constant reminder of the Earth's place in the cosmos, fostering a sense of global unity and environmental awareness. The sheer scale of the construction would be awe-inspiring, with the tether stretching into the distance, tapering to a point at the geostationary anchor. The physics of counterweights in a space elevator system is crucial for maintaining the structural integrity of the tether. A counterweight, typically placed at the geostationary orbit, provides the necessary centrifugal force to keep the tether taut. This counterweight could be a massive object, such as an asteroid or a specially constructed structure. The centrifugal force generated by the Earth's rotation acts to balance the gravitational pull, creating a dynamic equilibrium. This balance is delicate and requires precise engineering to ensure the stability of the system. The counterweight must be carefully positioned and designed to withstand the forces exerted by the tether and the ascending vehicles. Understanding and managing these forces is essential for the successful deployment and operation of a space elevator. Carbon nanotubes and graphene, the leading candidates. Carbon nanotubes and graphene stand out as the leading candidates for constructing space elevators and orbital habitats due to their exceptional strength-to-weight ratios and electrical conductivity. These materials are not just stronger than steel, they are also lighter, making them ideal for the immense structures required to reach geostationary orbit. A space elevator, for instance, would need a ribbon-like structure stretching over 100 kilometers into space. The sheer scale of this construction is mind-boggling, akin to building a bridge from the Earth's surface to the Moon. The view from such a structure would be breathtaking, offering a panoramic vista of the Earth below, the stars above, and the vast expanse of space in between. It's a perspective few have ever experienced, a humbling reminder of our planet's beauty and fragility. The physics behind these structures relies heavily on the properties of carbon nanotubes and graphene. These materials can withstand the tremendous tensile forces exerted by the Earth's rotation and the counterweight at the other end of the elevator. The counterweight, often envisioned as a space station or a captured asteroid, balances the system, ensuring the elevator remains stable. This balance is crucial, as any imbalance could lead to catastrophic failure. The elevator would use climbers, powered by lasers or other energy sources, to ascend and descend the ribbon. These climbers would carry people and cargo to and from orbit, revolutionizing space travel and commerce. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, is particularly promising due to its flexibility and strength. It can be used to create lightweight, durable structures that can withstand the harsh conditions of space. Carbon nanotubes, on the other hand, are cylindrical structures with remarkable tensile strength. They can be used to reinforce the elevator ribbon, ensuring it can support the immense weight and forces involved. Together, these materials offer a viable solution to the challenges of constructing space elevators and orbital habitats. Their unique properties make them indispensable in the quest to make space travel more accessible and affordable. The potential applications of these materials extend beyond space elevators. Orbital habitats, for example, could be constructed using graphene and carbon nanotubes to create lightweight, durable structures that can support human life in space. These habitats could serve as research stations, commercial centers, or even permanent settlements. The use of these materials would allow for the construction of large, complex structures that can withstand the rigors of space. The view from these habitats would be even more spectacular than from a space elevator, offering a 360-degree view of the Earth and the cosmos. It's a vision of the future that is both exciting and daunting, a testament to human ingenuity and ambition. Overcoming gravitational and centrifugal forces. The concept of space elevators and orbital habitats hinges on the delicate balance between gravitational and centrifugal forces. These structures aim to create a stable, continuous connection between Earth's surface and geostationary orbit, or to establish habitable environments in space. The sheer scale of such constructions is mind-boggling. A space elevator, for instance, would require a ribbon-like cable stretching over 100 kilometers into space. That's roughly one-quarter the distance between the Earth and the Moon. The base of this cable would be anchored to a ground station, while the other end would be attached to a counterweight far beyond geostationary orbit. From the vantage point of an orbital habitat, the view would be breathtaking. The Earth would loom large, filling a significant portion of the sky, with the curvature of the planet clearly visible. The International Space Station, for comparison, offers a stunning view, but it orbits at a mere 400 kilometers above the surface. An orbital habitat, on the other hand, would be situated at geostationary orbit, about 36 kilometers up. At this altitude, the Earth's rotation would be clearly perceptible, and the stars would shine with an intensity unmarred by atmospheric distortion. The physics behind counterweights in these structures is straightforward yet profound. A counterweight is essential to keep the space elevator's cable taut. It must be placed far enough from the Earth to ensure that the centrifugal force acting on it balances the gravitational pull. This balance is crucial for maintaining the elevator's stability. The counterweight could be a massive object, perhaps an asteroid captured and moved into position, or it could be a dense, compact structure made from materials like carbon nanotubes. The centrifugal force, generated by the Earth's rotation, would pull the counterweight outward, counteracting the gravitational force that seeks to pull it back toward the planet. In the case of orbital habitats, centrifugal force plays a different but equally vital role. These habitats would rotate to create artificial gravity, simulating the pull of Earth's gravity and making life more comfortable for inhabitants. The rotation would generate a centrifugal force that presses inhabitants against the habitat's inner surface, providing the sensation of gravity. The speed of rotation and the radius of the habitat would need to be carefully calibrated to achieve the desired gravity level. Too fast, and inhabitants might experience discomfort or even injury. Too slow, and the artificial gravity would be insufficient. The engineering challenges are immense, but the potential rewards are even greater. The role of geostationary orbits. Geostationary orbits, located about 786 kilometers above Earth's equator, play a pivotal role in the feasibility and functionality of space elevators and orbital habitats. This orbit is unique because it matches Earth's rotational period, allowing satellites and structures to remain fixed relative to a point on the planet's surface. For a space elevator, this means the tether can extend from the Earth's surface to a point in geostationary orbit, creating a stable and accessible pathway for transporting materials and people into space. The sheer scale of such a construction is mind-boggling. The tether would need to be thousands of kilometers long, made from materials strong enough to withstand the immense tensile forces and the harsh conditions of space. This requires advancements in materials science, particularly in the development of carbon nanotubes or other ultra-strong, lightweight materials. From the vantage point of a geostationary orbit, the view is nothing short of breathtaking. The Earth stretches out below in a vast, blue expanse, with continents and oceans visible in intricate detail. The curvature of the planet is clearly visible, and the thin, shimmering line of the atmosphere can be seen hugging the Earth's surface. This perspective offers a unique opportunity for scientific observation, weather monitoring, and communication. For orbital habitats, geostationary orbits provide a stable environment where structures can be constructed without the need for constant adjustments to maintain their position. This stability is crucial for creating habitable environments that can support human life for extended periods. The physics of counterweights in geostationary orbits is a fascinating aspect of space elevator design. To keep the tether taut and prevent it from collapsing under its own weight, a counterweight is placed at the end of the tether in geostationary orbit. This counterweight can be a massive object, such as a captured asteroid or a specially constructed module. The centrifugal force generated by the Earth's rotation acts on the counterweight, pulling the tether outward and keeping it under tension. This tension is essential for the safe and efficient operation of the space elevator. The counterweight must be carefully balanced to ensure that the tether remains stable and that the forces acting on it are evenly distributed. This delicate balance is achieved through precise engineering and continuous monitoring. In addition to their role in space elevators, geostationary orbits are also crucial for orbital habitats. These habitats would be large, rotating structures designed to provide artificial gravity and living spaces for humans. By placing these habitats in geostationary orbit, they can take advantage of the stable environment and the continuous view of the Earth below. The rotation of the habitat would create centrifugal force, simulating gravity and making it possible for inhabitants to live and work in a comfortable environment. The sheer scale of these habitats would be immense, with diameters of several kilometers and the capacity to house thousands of people. This would require advanced construction techniques and materials, as well as sophisticated life support systems to ensure the health and well-being of the inhabitants. Space elevator versus traditional rocket launch. The concept of a space elevator is a marvel of engineering, a ribbon of carbon nanotubes stretching from the surface of the Earth to a point in geostationary orbit, some 36.0 kilometers above the equator. This structure would be anchored to the Earth at a point near the equator, with a counterweight extending beyond geostationary orbit to ensure stability. The counterweight is crucial. It's not just a lump of metal, but a carefully calculated mass that keeps the entire structure taut, like a plumb bob on a string. The physics here is elegant. The centrifugal force of the counterweight's rotation keeps the elevator cable under tension, counteracting the gravitational pull on the Earth's end. In contrast, traditional rocket launches are a testament to brute force. Rockets work by expelling mass at high velocities, generating thrust that propels them upwards. The sheer scale of construction is immense, with rockets like the Saturn V standing at 110 meters tall, requiring millions of pounds of fuel to escape Earth's gravity. The view from orbit, a perspective that rockets provide, is breathtaking. Astronauts describe seeing the Earth as a blue marble, a fragile oasis in the vastness of space. This view is a stark reminder of our planet's beauty and vulnerability. The space elevator, if realized, would offer a more gentle and potentially cost-effective alternative. Climbers would ascend the cable at a steady pace, taking days to reach orbit rather than the mere hours of a rocket launch. The energy requirements would be significantly lower, as the elevator could be powered by solar energy or other sustainable sources. This would make space travel more accessible, opening up new possibilities for commerce, tourism, and scientific research. The view from the elevator would be equally spectacular, offering a slow, unhurried ascent into the stars. Passengers would witness the curvature of the Earth, the thin blue line of the atmosphere, and the endless expanse of space unfolding before them. However, the space elevator faces significant challenges. The materials required for the cable must be incredibly strong and lightweight, a challenge that has yet to be fully met. Additionally, the elevator would need to withstand the forces of Earth's rotation, atmospheric conditions, and potential impacts from space debris. Traditional rockets, while expensive and energy-intensive, are a proven technology. They can be launched from various locations and are not constrained by the need for a specific geostationary orbit. The choice between a space elevator and traditional rocket launch ultimately depends on technological advancements, cost-effectiveness, and the specific needs of space travel. Economic viability, cost-benefit analysis. The concept of space elevators and orbital habitats has long captivated scientists and futurists, but the economic viability of these megaprojects hinges on a complex cost-benefit analysis. The sheer scale of construction is mind-boggling. A space elevator, for instance, would require a ribbon-like structure stretching from the Earth's surface to geostationary orbit, roughly 36.0 kilometers up. This ribbon would need to be made of materials strong enough to withstand immense tensions, likely utilizing carbon nanotubes or other advanced composites. The counterweight at the end of the ribbon would be a massive structure, possibly an orbital habitat itself, ensuring the system remains balanced. The physics behind this is fascinating yet simple. The centrifugal force from Earth's rotation keeps the counterweight in place, creating a stable tether. Climbers would ascend and descend this tether, transporting people and cargo into space at a fraction of the cost of traditional rocket launches. From an orbital habitat, the view would be nothing short of breathtaking. Earth would hang below, a blue and white marble suspended in the void, with the curvature of the planet clearly visible. The stars would shine brightly, unfiltered by the atmosphere, and the sun would rise and set every 90 minutes. This vantage point offers more than just a stunning panorama. It provides a strategic location for scientific research, manufacturing, and even tourism. The economic potential is vast, but so are the initial costs. Building such structures would require unprecedented levels of investment, coordination, and technological innovation. The materials alone would be expensive, and the construction process would be slow and methodical, demanding precision at every step. The cost-benefit analysis must weigh these enormous upfront expenses against the long-term advantages. One of the most significant benefits is the reduction in the cost of accessing space. Traditional rocket launches are prohibitively expensive, with costs ranging from thousands to millions of dollars per kilogram of payload. A space elevator could drastically lower this cost, making space more accessible for commerce, research, and exploration. Orbital habitats could serve as hubs for manufacturing, taking advantage of the microgravity environment to produce materials and products that are difficult or impossible to create on Earth. Additionally, these habitats could support large populations, creating new markets and economic opportunities. However, the economic viability isn't just about the numbers. It's also about the vision and the willingness to invest in the future. The initial outlay would be substantial, but the long-term payoff could be transformative. Reduced launch costs would open up new industries, from space tourism to asteroid mining. Orbital habitats could become the next frontier for human settlement, offering solutions to overpopulation and resource scarcity on Earth. The key is to balance the immediate financial burden with the potential for long-term growth and innovation. It's a gamble, but one that could redefine humanity's relationship with space. The challenge lies in convincing investors and governments to take that leap of faith. Environmental impact, a greener path to space. The concept of space elevators and orbital habitats presents a fascinating intersection of technological advancement and environmental consciousness. These structures, if realized, would dwarf any human-made edifice on Earth. A space elevator, for instance, would stretch from the surface of the Earth to geostationary orbit, approximately 36,000 kilometers. The sheer scale of such a construction is mind-boggling, with the tether alone being several times wider than a human hair to maintain strength while keeping weight manageable. Orbital habitats, on the other hand, could be massive rotating cylinders or spheres, large enough to create artificial gravity and accommodate thousands of people. The view from these habitats would be breathtaking, offering a panoramic vista of the Earth, the stars, and the cosmos beyond. The physics behind these structures is equally captivating. A space elevator relies on a counterweight placed beyond geostationary orbit to keep the tether taut. This counterweight could be a massive object, perhaps an asteroid captured from space, or even a spacecraft. The tether itself would need to be made of a material strong enough to withstand the immense forces exerted on it, such as carbon nanotubes or graphene. The centrifugal force created by the Earth's rotation would help keep the tether under tension, making it possible for climbers to ascend and descend. Orbital habitats would use a similar principle, rotating to create artificial gravity through centrifugal force. The larger the habitat, the more comfortable the gravity would feel, reducing the health risks associated with long-term space travel. From an environmental perspective, space elevators and orbital habitats offer a greener path to space. Traditional rocket launches are incredibly polluting, with each launch releasing hundreds of tons of carbon dioxide and other greenhouse gases into the atmosphere. Space elevators, once operational, would provide a continuous and energy-efficient means of transporting people and materials into space. Solar power could be used to operate the climbers, further reducing the environmental impact. Orbital habitats could also contribute to sustainability efforts. They could serve as research stations for developing new technologies, such as advanced recycling systems and closed-loop life support, which could be applied on Earth to reduce waste and conserve resources. Additionally, these habitats could be used to grow food in space, reducing the strain on Earth's agricultural systems. The potential benefits of space elevators and orbital habitats extend beyond environmental concerns. They could revolutionize space travel and exploration, making it more accessible and affordable. This could lead to a new era of space tourism, scientific research, and resource utilization. The sheer scale of these structures would also inspire awe and wonder, reminding us of our place in the universe and the incredible feats that human ingenuity can achieve. The view from orbit, with the Earth suspended in the blackness of space, would be a humbling and transformative experience, fostering a greater appreciation for our planet and the need to protect it. Orbital habitats, expanding human presence. Orbital habitats represent a monumental leap in humanity's quest to expand its presence beyond Earth. These colossal structures, envisioned as rotating space stations, could provide artificial gravity and ample living space for thousands of people. The scale of construction is staggering. A typical orbital habitat might be several kilometers in diameter, requiring materials and resources equivalent to a small city. The construction process would involve assembling vast structures in orbit, using materials launched from Earth or mined from asteroids. The sheer size and complexity of these habitats would make them some of the most ambitious engineering projects ever undertaken. From orbit, the view would be breathtaking. Residents of orbital habitats would witness the Earth rotating below, its continents and oceans spread out in a mesmerizing display. The stars would be visible in all their glory, unobscured by Earth's atmosphere. The habitat itself would spin to create artificial gravity, with the outer rim experiencing the strongest centrifugal force. This rotation would also create a unique skyline, as the habitat's interior walls and structures would be visible from different angles, depending on one's position. The experience of living in such an environment would be unlike anything on Earth, offering a perspective that could foster a new sense of global and cosmic awareness. The physics behind orbital habitats is fascinating yet relatively straightforward. The concept relies on centrifugal force to simulate gravity. By rotating the habitat, objects and people inside are pushed outward against the walls, creating a sensation similar to gravity. The faster the rotation, the stronger the artificial gravity. However, too rapid a spin can cause discomfort, so a balance must be struck. Counterweights play a crucial role in maintaining the habitat's stability. These massive structures, often positioned at the ends of the habitat's arms, ensure that the center of mass remains balanced. This balance is essential for maintaining the habitat's orientation and preventing unwanted wobbling or tumbling. The counterweights also help distribute the forces generated by the habitat's rotation, ensuring a smooth and comfortable living environment. Living in an orbital habitat would present unique challenges and opportunities. The closed-loop ecosystems would need to be carefully managed to ensure a sustainable supply of air, water, and food. Advanced life support systems would be essential, recycling waste and maintaining a habitable environment. The habitats could serve as hubs for scientific research, industrial production, and even tourism. They might also act as stepping stones for further exploration of the solar system, providing a staging area for missions to the Moon, Mars, and beyond. The potential benefits of orbital habitats are vast, offering a glimpse into a future where humanity is no longer confined to a single planet. Designing habitable structures in space. The concept of designing habitable structures in space is a monumental task that pushes the boundaries of engineering and architecture. These structures, such as space elevators and orbital habitats, are not just about creating a place to live, but about constructing entire ecosystems that can sustain human life in the vacuum of space. The scale of these projects is staggering. A space elevator, for instance, would stretch from the surface of the Earth to geostationary orbit, approximately 36.0 kilometers. This is roughly 1/10 the diameter of the Earth itself. The sheer length of the cable alone presents immense challenges in terms of material strength and stability. Materials like carbon nanotubes are often discussed as potential candidates due to their exceptional tensile strength, but even these would need to be engineered to perfection to withstand the forces involved. From orbit, the view would be breathtaking. The curvature of the Earth would be visible, with the atmosphere appearing as a thin, fragile blue line. The stars would be ever-present, unobscured by the atmosphere, and the sun would rise and set every 90 minutes. This constant cycle of day and night would create a unique environment for inhabitants. The design of these structures would need to consider not just the physical aspects, but also the psychological impact on those living in such an environment. Large windows or viewing ports would be essential to provide a connection to the outside world and to help maintain a sense of orientation and time. The physics of counterweights in space elevators is a fascinating aspect of these designs. The counterweight at the end of the elevator cable serves a crucial purpose. It balances the centrifugal force exerted on the cable as the Earth rotates. This force is what keeps the cable taut and prevents it from sagging. The counterweight itself could be a massive object, perhaps even a captured asteroid, or it could be a structure designed to house additional facilities, such as solar power stations or research labs. The exact design would depend on the specific requirements and constraints of the project. The counterweight must be carefully calculated to ensure the stability of the entire system. Too little mass, and the cable would not remain taut. Too much, and the system could become unstable. Living in these orbital habitats would require a complete rethinking of how we design and build structures. Every aspect, from life support systems to waste management, would need to be carefully considered. The habitats would need to be self-sufficient, capable of producing their own food, water, and oxygen. This would likely involve advanced technologies such as hydroponics, algae-based life support systems, and water recycling. The design would also need to consider the effects of microgravity on the human body. Exercise equipment and artificial gravity systems would be essential to maintain the health of the inhabitants. The habitats would need to be modular, allowing for expansion and adaptation as needs change. This would involve designing structures that can be easily assembled and disassembled, using materials that are strong, lightweight, and durable. The goal is to create a sustainable, comfortable, and safe environment for human life in space. Artificial gravity, spinning habitats. The concept of spinning habitats to create artificial gravity is rooted in the principles of centrifugal force. As a habitat rotates, objects and people inside it experience an outward force that can simulate gravity. The faster the rotation and the larger the radius, the more realistic the gravity feels. For instance, a habitat with a radius of about 500 meters rotating once every 30 seconds would generate a gravitational pull similar to Earth's. This is because the centrifugal force is directly proportional to the radius and the square of the angular velocity. Constructing such habitats in orbit is a monumental task. The sheer scale of these structures is staggering. A typical spinning habitat designed to house a significant population would need to be several kilometers in diameter. This enormous size is necessary to ensure that the rotation doesn't cause disorienting effects like dizziness or nausea. The larger the radius, the smoother and more natural the artificial gravity feels. Building these habitats would require advanced materials and construction techniques, likely involving robotic assembly and in-situ resource utilization. The view from such a habitat would be breathtaking, offering a panoramic vista of Earth, the stars, and the vast expanse of space. The physics behind counterweights in spinning habitats is crucial for maintaining stability and balance. A counterweight is often used to balance the habitat and ensure smooth rotation. This counterweight can be a massive structure, perhaps a large asteroid or a specially designed module, positioned at the end of a tether opposite the habitat. The counterweight's mass and the length of the tether are carefully calculated to ensure that the system remains stable. The rotation of the habitat and counterweight around a common center of mass creates a stable, gravity-simulating environment. This setup allows for a comfortable living space where residents can move around freely, much like they would on Earth. Living in a spinning habitat would offer a unique experience. The view from orbit is unlike anything on Earth. Residents would witness the planet rotating below them, with day and night cycles occurring every 90 minutes as the habitat orbits Earth. The stars would be visible in all their glory, unobscured by Earth's atmosphere. This perspective would provide a profound sense of scale and isolation, reminding inhabitants of their place in the cosmos. The artificial gravity would make daily life feel normal, but the constant reminder of being in space would be ever-present. This blend of familiarity and otherworldliness would create a truly unique living environment. Life support systems, closed-loop ecosystems. In the vast expanse of space, life support systems are the backbone of any closed-loop ecosystem, especially in structures like space elevators and orbital habitats. These systems are designed to mimic Earth's biosphere, creating a self-sustaining environment where air, water, and food are continuously recycled. The scale of construction for such systems is monumental. A space elevator, for instance, would stretch from the Earth's surface to geostationary orbit, approximately 36.0 kilometers. The orbital habitats at the end of these elevators would need to be large enough to house entire communities, potentially kilometers in diameter. This sheer size is necessary to provide enough space for the complex ecosystems required to support human life. From orbit, the view would be breathtaking. The Earth would hang below, a blue and white marble suspended in the void. The curvature of the planet would be clearly visible, with the atmosphere a thin, fragile layer. The stars above would be a constant presence, unobscured by the atmosphere. This perspective would be a daily reminder of the isolation and the importance of the closed-loop systems keeping inhabitants alive. The physics of these systems is equally awe-inspiring. Counterweights at the end of the space elevator, possibly asteroids or massive structures, would balance the enormous tension in the elevator's tether. These counterweights would need to be precisely calculated to maintain the elevator's stability, ensuring it doesn't drift or collapse under the immense forces at play. The closed-loop ecosystems within these habitats would be a marvel of engineering and biology. Air would be recycled through plants and advanced filtration systems, removing carbon dioxide and replenishing oxygen. Water would be purified and reused in a continuous cycle, with any losses made up by extracting water from waste or incoming supplies. Food production would rely on hydroponics and aeroponics, growing crops without soil in carefully controlled environments. Waste management would be crucial, with every scrap of material repurposed or recycled. Even the waste heat from human activities and machinery would be captured and used to maintain the habitat's temperature. This intricate dance of systems would need to be perfectly balanced to support life in the harsh environment of space. Radiation shielding, protecting human colonies. Radiation is a significant challenge for human colonies in space. The Earth's atmosphere and magnetic field provide a natural shield against cosmic rays and solar radiation. However, in orbit, this protection is absent. To ensure the safety of inhabitants, effective radiation shielding is crucial. The scale of construction for such shielding is immense. Orbital habitats and space elevators require materials that can absorb or deflect radiation. Thick layers of materials like polyethylene, water, or even regolith from the moon or asteroids could be used. These materials are chosen for their ability to absorb radiation and their availability in space. The sheer volume needed means that construction would be a monumental task, involving advanced robotics and in-situ resource utilization. From orbit, the view is breathtaking. The Earth looms large, a blue and white marble suspended in the blackness of space. The curvature of the planet is visible, and the thin line of the atmosphere can be seen. This perspective underscores the vulnerability of human colonies in space. Without the Earth's protective layers, radiation levels are much higher. Solar flares and cosmic rays pose constant threats. Effective shielding is not just a technical challenge, but a necessity for survival. The construction of radiation shielding must be robust and reliable. It must withstand the harsh conditions of space while providing a safe environment for human habitation. The physics of counterweights in space elevators is fascinating. A space elevator relies on a counterweight at the end of a long tether to keep it stable. This counterweight can be a massive object, perhaps an asteroid or a specially constructed module. The counterweight's purpose is to balance the elevator's center of mass. This balance ensures that the elevator remains upright and stable. The counterweight also helps to manage the tension in the tether. The tether itself must be incredibly strong and lightweight. Materials like carbon nanotubes are often proposed for this purpose. They offer the necessary strength and flexibility. The counterweight and tether system must be designed to withstand the forces of radiation and micrometeoroid impacts. This adds another layer of complexity to the construction process. Radiation shielding in orbital habitats involves multiple layers of protection. The outer layer might consist of thick shielding to absorb high-energy particles. Inside, additional layers could provide further protection. Water is an excellent shielding material because it is effective at absorbing radiation and is readily available. It can be stored in large tanks around the habitat. Regolith from the moon or asteroids could also be used. It can be packed around the habitat to create a natural barrier. The design of the habitat must consider the distribution of these materials. The goal is to create a uniform shield that covers all sides. This ensures comprehensive protection against radiation. The construction of such shielding is a complex process. It requires precise engineering and careful planning. The result is a safe and habitable environment for human colonies in space. Psychological aspects: living in isolated environments. The sheer scale of space elevators and orbital habitats is staggering. A space elevator, for instance, would stretch from the surface of the Earth to geostationary orbit, approximately 36.0 kilometers. That's roughly 1/10 of the way to the moon. The counterweight at the end of the elevator would need to be massive, perhaps a captured asteroid or a large spacecraft, to keep the structure taut. The physics behind this is fascinating yet simple. The centrifugal force from the Earth's rotation keeps the counterweight in place, while the elevator itself remains anchored to the ground. It's a delicate balance, but one that could revolutionize space travel. Living in such an environment would offer a view unlike anything on Earth. From an orbital habitat, residents would see the planet in its entirety, a swirling blue and white marble suspended in the blackness of space. The International Space Station, ISS, provides a glimpse of this, but orbital habitats would be much larger, offering expansive windows and even outdoor observation decks. The sight of the Earth from orbit is known to evoke a profound emotional response, often referred to as the overview effect. This sense of awe and interconnectedness could be a significant psychological benefit, fostering a sense of global unity and environmental stewardship. However, isolation in such environments presents unique challenges. The closest neighbor could be hundreds or thousands of kilometers away, and communication with Earth would have a noticeable delay. This isolation could lead to feelings of loneliness and disconnection. To mitigate this, orbital habitats would need to be designed with psychological well-being in mind. Spacious living areas, opportunities for social interaction, and access to nature, even if it's just a small garden, could help. Regular communication with loved ones on Earth through advanced communication systems would also be crucial. Additionally, virtual reality could provide immersive experiences, allowing residents to visit different places or engage in activities that would otherwise be impossible in space. The psychological impact of living in such isolated environments is not to be underestimated. Studies of people living in Antarctica or on submarines have shown that prolonged isolation can lead to increased stress, sleep disturbances, and interpersonal conflicts. To address these issues, orbital habitats would need to have robust mental health support systems in place. This could include access to mental health professionals, counseling services, and even AI-driven support systems. Regular exercise, a balanced diet, and adequate sleep would also be essential for maintaining mental health. Moreover, the design of the habitat itself could play a role. Natural light, for example, has been shown to have a positive impact on mood and sleep patterns. By carefully considering these factors, it may be possible to create environments where people can thrive, even in the isolation of space. The role of 3D printing in space construction. In the vast expanse of space, traditional construction methods face immense challenges. The vacuum, extreme temperatures, and microgravity environment make conventional building techniques nearly impossible. This is where 3D printing steps in, offering a revolutionary approach to space construction. The scale of these projects is staggering. A space elevator, for instance, would stretch from the Earth's surface to geostationary orbit, roughly 36.0 kilometers. That's about 10 times the diameter of the Earth. Building such a structure would require materials stronger than anything currently available, and 3D printing could be the key to creating and assembling these advanced materials in situ. From orbit, the view of a space elevator under construction would be breathtaking. The tether, a ribbon-like structure, would extend from a base station on the Earth's equator, disappearing into the blackness of space. The counterweight at the end of the tether would be a massive structure, perhaps a captured asteroid or a specially constructed object, ensuring the tether remains taut. The physics behind this is fascinating yet simple. The counterweight's mass and the centrifugal force from the Earth's rotation keep the tether under tension, allowing it to remain stable. It's a delicate balance, much like a spinning top, where the right amount of force keeps it upright. 3D printing in space construction isn't just about building structures. It's about creating entire ecosystems. Orbital habitats, for example, would need to be large enough to simulate Earth's gravity through rotation, providing a comfortable environment for human inhabitants. These habitats could be printed using in-situ resources, like lunar or Martian regolith, mixed with binding agents. The process would involve layer-by-layer deposition, creating intricate, interlocking structures that could withstand the rigors of space. The sheer scale of these habitats would be mind-boggling. A single habitat could house thousands of people, with farms, parks, and residential areas all printed in one continuous process. Moreover, 3D printing allows for unprecedented design flexibility. Unlike traditional construction, where each component must be designed and built separately, 3D printing enables the creation of complex, interconnected structures in a single process. This could lead to innovative designs that maximize space and efficiency. For instance, a space habitat could have a honeycomb-like structure, providing strength and stability while minimizing the amount of material needed. The possibilities are endless, and the potential for creativity is vast. As we continue to push the boundaries of space exploration, 3D printing will undoubtedly play a pivotal role in shaping our future in the cosmos. In situ resource utilization, building with local materials. The concept of building space infrastructure using local materials, known as in situ resource utilization, ISRU, is a game-changer for constructing space elevators and orbital habitats. The sheer scale of these projects demands a shift from Earth-based manufacturing to utilizing resources found in space. For instance, the Moon and asteroids are rich in metals, minerals, and volatiles that can be harvested and processed to create construction materials. This approach drastically reduces the cost and complexity of launching materials from Earth, making large-scale space construction feasible. Picture the view from orbit, where the Earth is a breathtaking blue marble suspended in the void. From this vantage point, the construction of a space elevator or an orbital habitat is a monumental undertaking. The space elevator, a ribbon-like structure stretching from the Earth's surface to geostationary orbit, would require materials with extraordinary strength and durability. Carbon nanotubes, which can be synthesized from lunar or asteroid resources, are a prime candidate for this purpose. The elevator's counterweight, positioned beyond geostationary orbit, would need to be massive to maintain the system's stability. This counterweight could be a captured asteroid or a structure built from local materials, ensuring the elevator remains taut and functional. The physics of counterweights is straightforward yet crucial. A counterweight balances the forces acting on the space elevator, ensuring it remains stable and operational. The centrifugal force generated by the Earth's rotation provides the necessary tension. For an orbital habitat, the counterweight could be part of the habitat itself, creating a rotating structure that generates artificial gravity. This spinning habitat would resemble a giant wheel, with living spaces on the inner rim. The materials for these habitats can be sourced from nearby asteroids or the Moon, reducing the need for costly Earth launches. By leveraging local resources, the construction of these massive structures becomes not only possible, but also economically viable. The scale of these projects is hard to fathom. A space elevator, for example, would be thousands of kilometers long, dwarfing any man-made structure on Earth. The orbital habitats could be even more immense, providing living and working space for thousands of people. These structures would be visible from the ground, shimmering in the sunlight as they stretch into the heavens. The use of local materials ensures that the construction process is sustainable and efficient. By mining and processing resources in situ, the need for frequent and expensive launches from Earth is minimized. This approach not only reduces costs but also opens up new possibilities for exploration and colonization of space. The future of space infrastructure lies in the clever use of local resources, making the dream of large-scale space construction a reality. Space elevators as enablers of orbital habitats. The concept of space elevators has long captivated scientists and futurists, offering a revolutionary approach to space travel. These structures would consist of a cable extending from the Earth's surface to a geostationary orbit, with a counterweight beyond that point. The sheer scale of such a construction is mind-boggling. The cable alone would need to be thousands of kilometers long, with a width of several centimeters to withstand the immense tensions involved. Building such a structure would require materials with extraordinary strength-to-weight ratios, such as carbon nanotubes or graphene, which are currently in experimental stages. From an orbital perspective, the view from a space elevator would be breathtaking. Observers would witness the Earth rotating beneath them, with the curvature of the planet clearly visible. The elevator's cable would stretch into the distance, tapering off into the blackness of space. This vantage point would provide unparalleled opportunities for scientific observation and Earth monitoring. The physics behind the counterweight is fascinating yet simple. The counterweight ensures the cable remains taut by balancing the gravitational pull on the Earth's end. It must be placed at a point where the centrifugal force equals the gravitational force, typically at a distance of about 100 kilometers from the Earth's surface. Space elevators could serve as enablers for orbital habitats, providing a cost-effective and efficient means of transporting materials and people into space. These habitats, envisioned as large, rotating structures, would create artificial gravity through centrifugal force. They could house research facilities, industrial plants, and even residential areas. The construction of such habitats would be a monumental task, requiring vast amounts of materials and precise engineering. Space elevators would facilitate this process by offering a reliable and reusable infrastructure for lifting materials from Earth's surface. The economic implications are substantial. By reducing the cost of accessing space elevators could open up new markets and opportunities, fostering a robust space economy. The environmental impact of space elevators and orbital habitats is another critical aspect to consider. Traditional rocket launches are environmentally costly, releasing large amounts of greenhouse gases and other pollutants. Space elevators, on the other hand, would operate on a fraction of the energy, significantly reducing their environmental footprint. Additionally, orbital habitats could serve as hubs for space-based solar power, beaming clean energy back to Earth. This dual benefit of reduced emissions and increased renewable energy production makes the combination of space elevators and orbital habitats an attractive proposition for a sustainable future. The technological challenges are immense, but the potential rewards are even greater. Interplanetary transportation, gateway to the solar system. The concept of interplanetary transportation has long been a staple of science fiction, but recent advancements in technology and engineering are bringing it closer to reality. Space elevators and orbital habitats are at the forefront of this revolution, promising to open up the solar system for exploration and colonization. The sheer scale of these projects is staggering. A space elevator, for instance, would stretch from the surface of the Earth to geostationary orbit, approximately 36.0 kilometers above the equator. This is roughly 1/10 the distance from the Earth to the Moon. The counterweight at the end of the elevator would need to be massive, possibly a captured asteroid or a dedicated space station, to ensure the system remains stable. From orbit, the view would be breathtaking. The Earth would appear as a vast, blue marble suspended in the void, with continents and oceans visible in intricate detail. The curvature of the planet would be clearly evident, and the thin, shimmering line of the atmosphere would be visible, a fragile shield protecting life below. The stars, unobscured by atmospheric distortion, would shine with unparalleled clarity. This perspective would offer a profound sense of our place in the universe, a humbling reminder of the vastness of space and the relative insignificance of our planet. The physics behind space elevators and orbital habitats is complex but can be simplified for understanding. The key lies in the concept of a geostationary orbit, where a satellite orbits the Earth at the same rate as the planet's rotation, effectively remaining fixed above a single point on the equator. This is achieved by balancing the gravitational pull of the Earth with the centrifugal force generated by the satellite's motion. A space elevator would use a tether, likely made of a super-strong material like carbon nanotubes, to connect the Earth's surface to this geostationary orbit. The counterweight at the end of the tether would ensure the system remains in equilibrium, allowing for the efficient transport of people and goods into space. Orbital habitats, on the other hand, would be large, rotating structures designed to provide artificial gravity for their inhabitants. These habitats would need to be massive to generate sufficient centrifugal force to simulate Earth-like gravity. For example, a habitat with a radius of 500 meters would need to rotate once every 40 seconds to achieve 1 g of gravity. The sheer scale of these structures would make them visible from the Earth's surface, appearing as bright, moving stars in the night sky. The construction of such habitats would require advanced materials and technologies, but the potential rewards are immense. They could serve as waypoints for interplanetary travel, providing a place for astronauts to rest and resupply before continuing their journey to other planets or moons. Legal and regulatory frameworks governing space infrastructure. The sheer scale of space elevators and orbital habitats demands a robust legal and regulatory framework to govern their construction and operation. These structures will dwarf anything ever built by humans. A space elevator, for instance, would stretch from the Earth's surface to geostationary orbit, approximately 36.0 kilometers. That's roughly 10 times the diameter of Earth. The counterweight at the end of the elevator would need to be massive, perhaps a captured asteroid or a large space station, to balance the immense tension in the tether. The physics here is straightforward. The center of mass of the system must be directly above the anchor point on Earth to maintain stability. This ensures that the elevator remains taut and doesn't drift off into space or crash back to Earth. From orbit, the view would be breathtaking. The curvature of the Earth would be clearly visible, with cities and landmarks stretching out below. The blackness of space would provide a stark contrast to the vibrant blues and greens of our planet. The scale of the construction would be evident, with the tether disappearing into the distance, tapering to a point at the horizon. The orbital habitat, a massive rotating structure designed to provide artificial gravity, would be a marvel of engineering. Its spinning motion would create a centrifugal force, simulating gravity and allowing inhabitants to live and work in a more familiar environment. The legal and regulatory frameworks for such infrastructure are still in their infancy. Current space law is primarily governed by the Outer Space Treaty, which is woefully outdated for the complexities of large-scale space construction. The treaty establishes that no nation can claim sovereignty over celestial bodies, but it doesn't address the ownership and operation of structures like space elevators or orbital habitats. New laws and regulations will need to be developed to address issues such as liability, safety, and environmental impact. For example, who is responsible if a space elevator fails and causes damage on Earth? How can we ensure the safety of workers and inhabitants in these massive structures? What are the environmental implications of such large-scale construction? International cooperation will be crucial in developing these frameworks. The sheer scale and cost of space elevators and orbital habitats mean that they will likely be international projects, involving multiple nations and private entities. This cooperation will need to extend to the legal and regulatory realm as well. Agreements will need to be reached on issues such as jurisdiction, dispute resolution, and the sharing of resources. The complexity of these issues cannot be overstated. It will require input from legal experts, engineers, scientists, and policymakers from around the world. The goal is to create a framework that is flexible enough to adapt to the rapidly changing landscape of space technology, while also providing the necessary guidelines to ensure safety and sustainability. International collaboration, a unified vision for space. The concept of space elevators and orbital habitats has captivated scientists and engineers for decades, but the sheer scale of these projects demands international collaboration. A single spacefaring nation or corporation couldn't hope to tackle such monumental tasks alone. The construction of a space elevator, for instance, would require materials stronger than any currently in use, likely involving carbon nanotubes or other advanced composites. These materials would need to be manufactured on an unprecedented scale, a feat that would necessitate global cooperation and investment. From orbit, the view of a completed space elevator would be breathtaking. The structure would stretch from the surface of the Earth to a point far beyond geostationary orbit, a thin, glinting thread against the blackness of space. The counterweight at the end of the elevator, perhaps a captured asteroid or a massive space station, would serve a crucial purpose. It keeps the elevator's center of mass well above geostationary orbit, ensuring the structure remains stable. The physics here is straightforward. The counterweight's mass pulls the elevator outward, while the Earth's gravity pulls it downward, creating a balance that keeps the elevator taut. Orbital habitats, too, would benefit from a unified vision. These massive structures, potentially housing thousands of people, would need to be constructed in space, using materials launched from Earth or mined from asteroids. The scale of these habitats is hard to fathom. They would be rotating to create artificial gravity, their interiors filled with lush greenery and bustling cities. From the surface, they might appear as bright stars, slowly moving across the night sky. But from the surface of the habitat itself, the view would be even more spectacular. The Earth would hang in the sky, a blue and white marble, while the stars would blaze brightly, unfiltered by an atmosphere. International collaboration would also drive innovation. Different countries bring unique strengths to the table. Some might excel in materials science, others in robotics or space launch technology. By working together, these nations could share their expertise, accelerating the development of space elevators and orbital habitats. Moreover, such collaboration would foster goodwill and mutual respect, uniting humanity in a shared endeavor. It's not just about the technology, it's about the vision. A unified vision for space, where nations work together to push the boundaries of what's possible. Potential challenges and mitigation strategies. The sheer scale of constructing a space elevator is mind-boggling. The structure would need to stretch from the Earth's surface to geostationary orbit, approximately 36.0 kilometers. To put that into perspective, it's almost 3 times the diameter of the Earth. The materials required would need to be incredibly strong and lightweight, as the elevator would face immense tensile stresses. Carbon nanotubes, or graphene, could be potential candidates, but producing and assembling these materials on such a massive scale is a challenge that hasn't been overcome yet. One of the most significant challenges is the need for a counterweight at the end of the elevator in geostationary orbit. This counterweight would need to be massive, perhaps a captured asteroid or a specially constructed object, to provide the necessary centrifugal force to keep the elevator taut. The physics here is straightforward. As the Earth rotates, the counterweight would spin around the planet, creating a centrifugal force that balances the gravitational pull, keeping the elevator cable under tension. However, getting such a massive object into position is a monumental task. The view from an orbital habitat at the top of a space elevator would be breathtaking. From this vantage point, the Earth would fill a significant portion of the sky, with the curvature of the planet clearly visible. The International Space Station, for comparison, orbits at about 400 kilometers, where the Earth appears to curve more subtly. At 36.0 kilometers, the perspective would be vastly different, offering a stunning, panoramic view of the planet. This vantage point could also provide unique opportunities for scientific research and Earth observation. Mitigation strategies for these challenges involve a combination of technological innovation and incremental progress. For the materials science hurdle, ongoing research into advanced materials like carbon nanotubes and graphene is crucial. These materials need to be not only strong, but also cost-effective to produce on a massive scale. For the counterweight, one strategy involves using a captured asteroid, which would require advancements in asteroid mining and space propulsion technologies. Alternatively, a specially constructed counterweight could be assembled in orbit using materials launched from Earth. Another challenge is the dynamic environment of space. The elevator would need to withstand micrometeoroids, space debris, and the harsh radiation of the Van Allen belts. Mitigation strategies include developing advanced shielding materials and redundant systems to ensure the elevator's integrity. Additionally, the elevator would need to be designed to withstand the stresses of Earth's weather and seismic activity at the ground anchor point. This requires robust engineering solutions and extensive testing. The construction process itself presents a significant challenge. Building such a massive structure in space would require advanced robotics and autonomous systems. These systems would need to operate independently, as real-time control from Earth would be impractical due to the time delay. Developing and testing these technologies will be a critical step in making space elevators a reality. Furthermore, the economic viability of space elevators will depend on their ability to reduce the cost of space travel significantly. This will require not only technological advancements, but also innovative business models and international cooperation. The future, a network of space elevators and habitats. The concept of a network of space elevators and orbital habitats is not just science fiction. It's a vision that scientists and engineers are actively working towards. Space elevators, as envisioned, would be colossal structures stretching from the Earth's surface to geostationary orbit, roughly 36.0 kilometers up. The scale of construction is mind-boggling. The tether alone would need to be incredibly strong and lightweight, with materials like carbon nanotubes being prime candidates. These structures would dwarf any man-made object ever built, making the Burj Khalifa look like a mere speck in comparison. From an orbital habitat, the view would be breathtaking. The Earth would hang below, a vast blue and white marble suspended in the blackness of space. The curvature of the planet would be clearly visible, with cities, oceans, and weather patterns unfolding in real time. The International Space Station offers a glimpse of this perspective, but orbital habitats would provide a more stable and expansive vantage point. The stars above would be ever-present, unobscured by Earth's atmosphere, offering a view of the universe that few have ever witnessed. The physics behind space elevators is fascinating yet relatively simple. The key lies in the concept of a geostationary counterweight. The tether would be anchored to the Earth at the equator, with a counterweight placed at the outer end. This counterweight would experience a stronger centrifugal force due to its greater distance from the Earth's center, effectively pulling the tether taut. The centrifugal force counteracts gravity, keeping the tether under tension. This balance allows for the elevator to ascend and descend without the need for rocket propulsion, making space travel far more energy efficient. Orbital habitats, on the other hand, would be massive rotating structures designed to simulate gravity through centrifugal force. These habitats could be large enough to house entire communities, complete with parks, farms, and residential areas. The rotation would create artificial gravity, making life more comfortable for long-term inhabitants. The scale of these habitats would be enormous, potentially kilometers in diameter, providing ample space for human settlement. The construction of such habitats would require advanced materials and technologies, but the potential benefits are immense. They could serve as waypoints for deep space exploration, research stations, or even permanent homes for those seeking to live among the stars. As we wrap up our journey into the future of space elevators and orbital habitats, let's take a moment to soak in the sheer scale of what we're talking about. Imagine a structure so tall, it dwarfs even the tallest mountains on Earth, stretching over 100 kilometers into the sky. That's the kind of engineering marvel we're discussing here. The view from one of these orbital habitats would be nothing short of breathtaking. You'd be looking down at our planet from a vantage point where the curvature of the Earth is clearly visible, and the stars above are a constant, dazzling spectacle. Now, let's talk about the physics behind it. The key to making a space elevator work is the counterweight. This massive object at the end of the elevator's cable would be placed in geostationary orbit, where it would balance the entire structure. It's like a giant, cosmic seesaw, with the counterweight keeping everything in perfect equilibrium. The elevator itself would use advanced materials, like carbon nanotubes, to create a cable strong enough to withstand the immense forces at play. To summarize, we've explored how space elevators could revolutionize space travel, making it cheaper and more accessible than ever before. Orbital habitats could provide us with new homes among the stars, offering stunning views and a unique perspective on our place in the universe. The physics behind these concepts is complex, but the potential benefits are enormous. If you're as excited as we are about the future of space exploration, then stay tuned. We've got plenty more content coming your way, diving deeper into the science and technology that will shape our journey to the stars. Don't forget to like, share, and subscribe to join us on this incredible adventure. Together, let's reach for the stars and make the impossible possible. See you in the next video.